All right, so here's the continuation of section 10.4. We are not going to cover something this book covers. It's called mean absolute deviation or variance. Those were measures of spread. We're not going to cover those. Okay, I mentioned variance is just the standard deviation squared, so it's not really that big of a deal. But we're not going to cover the mean absolute deviation. That's just not really necessary. This section is long enough. Okay, next up is something called that falls under something called measures of position. A percentile. You may have heard percentiles or percentile ranks given when you took a standardized test like the ACT or the SAT, something like that. Also, if you have at a pediatric office, when you have a baby and you take them in and they tell you, oh, their weight is in the 75th percentile, their head circumference is in the 98th percentile, they tell you things like that. The percentiles are not percentages. Okay? They're not the same thing. A percentile is a measure of relative standing. Okay? What a percentile tells you is the percent of data that is below you. Okay? So a percentile of a data point indicates the percent of data values in a set that are below that particular value. So it's not the same as a normal percentage. It is a measure of relative standing. That means how you performed relative to a group. So for instance, if your child's birth weight is in the 90th percentile, this means that 90% of other babies' birth weights are below that of your baby. Okay, so that's all it means. 90th percentile means that 90% of other birth weights are below you. So a percentile is a percent below you. Percentiles tell you nothing specific, just how you relate to others in that same group. So for instance, your ACT score. Let's say your ACT score is in the 85th percentile. Does this mean you scored an 85% on the ACT? No. This tells you nothing about your score. Okay, 85th percentile tells you nothing about your score. You could have stunk up the place with your ACT score. I mean, it could have been garbage, but you still did better than 85% of the other people who took that same test. Okay? So it just means 85% of the people who took that test scored below you. You did better than 85% of the other people. So it just tells you how you compare to others. So let's talk about how to calculate a percentile rank. So example 10, Elena ranked 100th out of her graduating class of 600, and Maria ranked 150th out of her graduating class of 750. Find each student's percentile rank. So in order to compare them to each other, their relative standing, Elena doesn't get to say, oh, well, I deserve the scholarship because I was 100th in my class, and Maria was only 150th, so I did better than her. Well, they were out of a different total. So here's what we're going to have to find. A percentile is a percent below. Okay, so a percentile is a percent below. So first off, we're going to have to find the number of students who were below her. Well, if she was 100 out of 600 students, then there's 500 students below her. So there's the number of students that were below her. Dividing that by the total will give us a percent. Well, it'll give us a decimal that we can then move the decimal place to 2 places to the right and get a percent. So 83.3% of students were below Elena. That means she's in the 83rd percentile for her class. For Maria, how many students were below her? Well, she was 150 out of 750, so there were 600 below her. So again, we've got the number of students that were below her divided by the total number of students in her graduating class. We get 0.8. Remember, to change it to a percent, you move that decimal place 2 places to the right. Change the decimal to a percent. We get 80%, or the 80th percentile. So, relatively speaking, Maria performed better because she's in the 80th percentile of her class, whereas Elena is in the 83rd percentile of her class. So it's a measure of how you performed relative to others, how you compare to others. Okay, so that's about all you need to know about the percentiles, that they are the percent of people below you, okay, and how to find a percentile. Last up in this section is something called the normal distribution. Now, it's called this because when you look at normal everyday data, like people's weights, people's heights, their IQs, their shoe size, things like that, the heights of trees, that kind of natural, the stuff that naturally occurs, then this stuff tends to be normally distributed, or this nice little bell-shaped curve. It is a bell-shaped curve that is symmetrical on both sides of the mean. The mean is right there in the middle, and it is very symmetrical about the mean. It may not be a perfect normal distribution, but it's pretty darn close. Now, here's how this distribution shakes out. Okay? You're going to want to keep this handy because you're going to need to reference this a bunch, okay? And what I'm going to do is I've got a sheet that will help you keep all this stuff straight, that you can use as a quick reference guide. Flip. Let's see if I can find it. There it is. So I'm going to post that with these lecture notes so that you can have this as a quick reference guide to hang on to. So you can see that's the mean right there. See the X bar? So we're going to keep this handy for when we do examples. What this 1, 2, 3 is telling us is how many standard deviations data is from the mean. In typical or normally distributed data, 34% of the data is 1 standard deviation above the mean. That means whatever the mean happens to be, whatever the standard deviation happens to be, that 1 above and 1 below each make up 34%. So we say that within 1 standard deviation is 68% of the data. 95% of the data falls within 2 standard deviations, and 99.7, some books say 99.8, of the data lies within 3 standard deviations of the mean. This is going to be easier seen than said. Okay, this doesn't make a whole lot of sense without actual, data to look at. So let's just go ahead and flip. So that's the stuff that I was just saying. There, I just decided to write it. On an exam, the mean is 79 and the standard deviation is 3.5. If a grade of A is given to students who score 2 standard deviations above the mean or higher, what is the lowest score needed to get an A? So here's what this means. If the scores are normally distributed, then we have this mean of 79. The standard deviation is 3.5. So this number right here is going to be 79 plus 3.5. So that'll be 82.5. All right, let's keep adding. If we add 3.5 again, that's going to be, 82.5? So it's 83, 84, 85, 86. this direction, if I subtract 3.5, I'm going to get, I think, 75.5. Let me check that out just to make sure, because I don't want to make that mistake. So 75.5. If I subtract 3.5 again, that's going to give me 72. So here's what this means. This is that 34%. So 68% of the test scores fall between 75.5 and 82.5. 95% of the test scores are going to fall between 72 and 86. Now I could keep going and add 3.5 again, subtract 3.5 again here. But it says that a grade of A is given to anyone who scores 2 standard deviations above the mean or higher. So here's the mean. So there's the mean. Here's 1 standard deviation. Here's 2 standard deviations, because I added this standard deviation once and then again. So what this tells us is that anybody that makes an 86 or higher gets an A. This is what's known as grading on a curve. A lot of students mistakenly think that, oh, can you just curve our grades? When some students say curve our grades, they think, oh, just bump everybody's grade up. That's actually not what curving means. Curving grades means that you fit your grades to a normal distribution curve, okay? So that even if your grades are not in this bell-shaped curve, you fit them to that. Now, if that means that you got to bump some people down here up a little bit, okay? But it might mean that if you have too many A's or B's, you got to bump some of them down. That's, because otherwise you end up with data that's kind of skewed to the right. Okay. The heights of 8,585 men are normally distributed with a mean of 68 inches and a standard deviation of 3 inches. Now, 68 inches, do you guys know how tall that is? 60 inches is 5 foot, so that's 5 foot 8 inches with a standard deviation of 3. What percent of men are between 5'5" and 5'11"? All right, let's reference this guy right here. So here's what we have. We got that normal distribution thing going on here. The mean right there in the middle is that 5'8", and each group that we go out is going to go out by 3 inches. So let's go ahead and draw a curve to go with this specific data. So if we come over here and we draw normal curve, doesn't have to be pretty. That mean was 5'8", and my standard deviation was 3 inches. Okay, so 1 standard deviation above is going to add 3 inches. So that's 5'11". Adding another standard deviation is going to add another 3 inches. Okay, 5'11", if you add 3 inches, that's going to be 6'2". Right, because 12 inches is a foot. So you add 1 inch and you're at 6 feet. So you add 3, you get 6 foot, 6'2". If I added another one, now we're at 6'5". That's 3 standard deviations up. Let's go below the mean. This is one standard deviation below. That's subtracting this standard deviation of 3. If I subtract 3 inches, now we're at 5.5. Subtract 3 again, now we're at 5.2. Subtract 3 again, now we're down to, what, 4.11? All right, so comparing this to this, here's what we have. Within one standard deviation, one above and one below, is this 68% of data. Remember, this is 34 and this is 34. Between here and here, within 2 standard deviations, is 95%, and then within 3 standard deviations is the 99, what did they use, 7 or 8? Oh, they used 7, okay. Oh, well that stinks, because the one that I found online said 8. That's cool. Watch me fix that. Boom, problem solved. Solving problems. Okay, coming back over here. What percent of men are between 5.5 and 5.11? Okay, between 5.5 and 5.11, that is within one standard deviation. That is one standard deviation added, one standard deviation subtracted. So, what percent? 68%. How many men? Pay attention to this. This one said what percent. This says how many. We're going to find the percent, and then we're going to take that percent of our total. All right, so between 5.2 and 6.2. Well, between 5.2 and 6.2 is that within 2 standard deviations. See, there's our 2 standard deviations. That's the 95%. So this is going to be 95% of the total, 85. So that's going to be 0.95 times 85. So what's 95%? 85. That's about 81557. So let's round it to the nearest person. The difference being that the first one asked me for a percent, the second one asked for how many. So I took, a percent of this total right there. How many men are less than 5'2"? This one's tricky. So less than 5'2". So here's the 5'2", right there at that second standard deviation below the mean. How many men are below that? So it's that region and that region. So you can see that. So we got that and that. That's the 2 regions that are below 5'2". I haven't bothered to shade in the other regions because the other regions all kind of fell into this, this red stuff. But these 2, if we compare it to this, then we would be making a mistake because this uses 0.15. So we'll throw a 5 on here. And we'll throw a 5 on here. There we go. So what we're going to do, these 2 regions right here, are that below 5'2". So we're going to add up those 2 percents and then take that as a decimal multiplied by the total. Right, so that's going to be that 0.15% plus 2.35%. Scratch this up a little bit and run out of space. I hate when I make a mistake with the pen. So if we add those together, we're going to get, what, 2.5% of 8,585. So that's going to be 0.025 times 8585. I'll do that computation real quick for us. That is about 215 people, or 215 men, that are shorter than 5'2". That seems reasonable, right? That's kind of short. So, you know, if you're talking about 8,000 guys, it's probably reasonable that you're going to have, you know, very few of them be 5'2" and shorter. It also kind of makes sense that most of the guys, you know, most men are going to be between 5'2" and 6'2". So think about the reasonableness of your answer too when you're doing this. So let's see, this was 2.4%. So I went over here, sorry, 2.35 and 0.15. My mistakes here. Just know that I'm forgiving of you guys' mistakes as well, because, you know, none of us are perfect. Alright, so 2.35 and then 0.15. Probably better to look over here at this one, since I've since realized that that should be a 3.5. I thought this was so pretty. I was like, oh, this is so pretty. I'm going to blow this up, and then they can have this to a quick reference, but then this book goes and uses an 8 instead of a 7 like your book does. So these are all kind of off. So I'll change those before I post it. Anyway, alright, that's about enough of this section. Whew, I don't know about you guys, but I am sick of this section already. Very, very long section. Tried to make it as bearable as possible. Hope it wasn't too painful. So this concludes section 10.4.